Again, welcome to operating system called CS332. And these lectures, we're going to continue with the virtual memory, which was covered in chapter 8 of our course textbook. And the first part, which is the unit 8 part 1 lectures, we discuss about the computer hardware and the control structure. So we discuss about paging, segmentation concept, also mapping, and the address, physical address, and also the logical address translation. But in this session, we continue with the software aspect of it. So our main objective is operating system software, fetch policy, placement policy, replacement policy, resident set management, cleaning policy, and also the load control. So we know the design of the memory management portion of an operating system depends on three fundamental areas of choice. First, whether or not to use the virtual memory techniques. Second, the use of the paging or segmentation, or both. And thirdly, the algorithm employed for various aspects of the memory management. So these are the three choices. Now, the choices made in the first two areas will, again, aspect of memory management would depend on the hardware platform available. So the choice of whether or not to use virtual memory techniques and also the use of paging or segmentation will depend on the hardware platform available. So the earlier Unix implementation did not provide virtual memory because the CPU or the processors on which the system ran did not support the paging or segmentation. So neither of these techniques is practical without hardware support for addressing the translation and other basic functions. When we discuss about translation in concept of virtual memory, translation of the physical address and the logical address, and also the mapping, which make it possible. If the processor doesn't support it, again, we cannot implement any of these two methods. Now, two additional comments about the first two items in the preceding is that first, with the exception of operating system, for some of the older personal computers, such as MS-DOS or specialized system, all important operating systems provide virtual memory. Secondly, pure segmentation systems are becoming increasingly rare. Most of the time now we have combination of both segmentation and paging, as we discussed in our previous lectures. So when segmentation is combined with paging, most of the memory management issues confronting the operating system designers are in the area of paging. So we're going to concentrate in this section on the issues associated with paging. So the choices related to the third item, which is the algorithm employed for various aspects of memory management, are the domain of the operating system software and also are the subject of this section. So again, this section, we are going to focus on the algorithm employed for various aspects of memory management, which again, based on operating system software. So from this table, we list the key design elements that we're going to examine. Now, in each case, the key issue is one of performance. First, we would like to minimize the rate at which page faults, the page faults again occurs, because page faults causes considerable software overhead. So at a minimum, the overhead includes deciding which resident page or pages to replace, and also the I/O of exchanging pages. Also, the operating system must schedule another process to run during the page input and output, causing a process switch. Also, we would like to arrange matters so that during the time that a process is executing, the probability of referencing a word on a missing page is minimized. And that's the concept again, page fault. So in all of the areas referred in this table, there is no a definite policy that will work best. And as we shall see later, the task of memory management in paging environment is very complex. Furthermore, the performance of any particular set of policy depends on the main memory size and also the relative speed of the main and also the secondary memory. Also the size and the number of processing competing for resources, and also the execution behavior of individual programs. So the characteristics here depends on the nature of the application, also the programming language, and also the compiler employed, the style of the programmer who wrote it, and for an interactive program, the dynamic behavior of the user. So here again, we shouldn't expect no final answers here or anywhere. So for example, for smaller system, the operating system designer should attempt to choose a set of policy that seems good over a wide range of conditions based on the current state of knowledge. And also for larger systems, particularly the mainframes, the operating system should be equipped with monitoring the control tools that allow the site manager to tune the operating system to get a good result based on the site condition. So these are the operating system policy. We shall go through each one. The first policy, again, we discussed about the demand paging and pre-paging. We also have the placement policy, replacement policy, resident set management, the cleaning policy, and also load control. So that's our main objective. So we start with the fetch policy. And here we say the fetch policy determines when a page should be brought into the main memory. And the two common alternatives are demand paging and also pre-paging. So determine when page should be brought into memory. Then the two main types are again the demand paging and also the pre-paging. So with the demand paging, a page will be brought into a main memory only when a reference is made to a location on that page. So that's why again it's called demand paging, when it's demanded. So here we say only brings page into main memory when a reference is made to a location on the page. Now, if other elements of memory management policy are good, the following should happen. When a process is first started, there will be a flurry of page faults. As more and more pages are brought in, the principles of locality suggest that most future references will be to the page that have recently been brought in. After a time, matters should settle down and the number of pages fault should drop to a very low level. So many page faults when process is first started. The concept of principles of locality suggests that as more and more pages are brought in, again, most future references will be to pages that have recently been brought in. And the page fault again should be dropped to a very low level. Now, the concept of pre-paging. Here, pages other than the one demanded by a page fault are brought in. So pages other than the one demanded by page fault are brought in. So pre-paging exploits the characteristics of most secondary memory devices, such as the disk, which have a seek times and rotational latency. Also, if the pages of a process are stored contiguously in secondary memory, then it is more efficient to bring in a number of contiguous pages at one time rather than bringing them in one at a time over an extended period. Of course, this policy is ineffective if most of the extra pages that are brought in are not referenced, so which means are not used. So prepaging policy could be employed either when a process first starts up, in which case the programmer will somehow have to designate a desired pages, or every time a page fault occurs. This later course will seem preferable because it is invisible to the programmer. So prepaging should not be confused with swiping. When a process is swiped out of a memory and put in a suspended state, all of its resident pages are moved out. But when a process is resumed, all of the pages that were previously main memory are returned back to the main memory. So next we talk about the placement policy. Now, placement policy normally would determine when in real memory a process piece is to reside. So that's the concept, placement policy. Determine when in a real memory a process piece is to reside. So in a pure segmentation policy, which again we discussed in our previous lecture, the placement policy is an important design issue. Policies such as best fit or fit first and so on, which again were discussed in chapter 7 of our course textbook, are the possible alternatives. Chapter 7, we discussed about the main memory management. However, for a system that uses either pure paging or paging combined with segmentation, placement is usually irrelevant because the address translation hardware and the main memory access hardware can perform their functions for any page frame combination with equal, again, efficiency. Also, there's one area in which the placement does not become a concern, and this is a subject of research and development. And this is what is so-called the non-uniform memory access, NUMA, non-uniform memory access system. And system and automatical placement strategies is desirable. So the distributed, the multiprocessor, the shared memory of the machine can be referenced by any processor on the machine. By the time for accessing a particular physical locations varies with the distance between the processor and the memory. We know when the distance are very big or wide, and the time of accessing again increases. So performance will depend heavily on the extent to which data reside close to the processor that use them. So again, if where the data is resided is very close to the CPU, then access time reduce, say quick access. If the distance is longer, then the access time increases. So for NUMA, or non-uniform memory system, an automatic placement strategy is desirable. It's very desirable to design pages to the memory module that provide the best performance. Next, we talk about the replacement policy. And in most operating systems, the treatment of memory management include a section entitled replacement policy. So replacement policy normally deal with the selection of a page in a main memory to be replaced when a new page must be brought in. So this topic is sometimes difficult to explain because several interrelated concepts are involved. So example, how many pages frames are to be allocated to each active process, or whether the set of pages to be considered for replacement should be limited to those of the process that cause the page fault or encompasses all the page frames in memory. So among the set of pages considered, which particular page should be selected for replacements? So these are very difficult issues we have to answer. So we shall refer to the first two concepts as resident set management, which is again dealt with in the next subsection. We're going to discuss about again the concept of resident set management. And we are going to reserve this term, placement policy, for the third concept, which is discussed in this subsection. Now, one restriction on replacement policy needs to be mentioned before looking at the various algorithms, the concept of frame locking. So some of the frames in the main memory may be locked. Now, when the frame is locked, the page currently stored in that frame may not be replaced. So much of the kernel of the OS, as well as key control structures, are held in the locked frames. In addition, input and output buffers and other time critical areas may be locked into the main memory frames. So locking is achieved by associating a lock bit with each frame. So this bit may be kept in a frame table or as well as being included in the current page table. So now we're going to start with the basic algorithms. And so again, regardless of the resident set management strategy, which we are going to discuss in the next subsection, there are certain basic algorithms that are used for the selection of page to replace. So replacement algorithms that have been discussed in the literature include optimum, least recently used, first in, first out, and also the clock. We shall go through each one. So again, the optimal policies select for replacement that page for which the time to the next reference is the longest. So here again, we say the optimal policy selects for replacement that page for which the time to the next reference is longest. And also it can be shown that this policy results in the fewest number of page faults. This policy also is impossible to implement because it will require the operating system to have a perfect knowledge of future events. However, it does serve as a standard against which to judge a real-world algorithms. And so the diagram here gives an example of an optimal, again, policy. So the example here, here we have all the three methods, the optimal, least, FIFO, and the clock. So here we have a phase allocation, phase frame allocation, or the phase resident set size for this process of 3 frames. Now, the execution of the process requires references to 5 distinct pages. So we can see 5 distinct pages. This page address stream formed by executing the programs. Again, 2, 3, 2, 5, 2, 4, 5, and the rest. So this means that the first page which is referenced is 2. The second page is referenced is 3, and so on until then. So the optimal policy procedure, the optimal policy produces 3 page faults after the frame allocation has been filled. So F equal to the page fault occurring after the frame allocation is initially filled, which we have the F here because it's initially filled, and also at the second. and with the list and also FIFO and the clock. So, and we'll go through this one at a time. So the next is the least recently used algorithm. And the least recently used policy normally will replace the page in memory that has not been referenced for a longest time. So that's why we call this algorithm a least recently used. Replaces the page that has not been referenced for the longest time. And also by the principles of locality, which we studied in our previous lectures, this should be the page least likely to be referenced in the near future. And also, in fact, the least recently used, or LRU policy does nearly as well as the optimal policy. The problem with this approach is the difficult in implementation also, same as the previous one. So again, one approach will be to tag each page with the time of its last reference, and this will have to be done at each memory reference, both instruction and data. Even if the hardware will support such a scheme, the overhead will be very high. Or here we say this requires a great deal of overhead. The next one is the first in, first out policy, which treat the page frame allocated to a process as a circular buffer. And this concept we discussed in data structure class and circular queue. So to be more or less a circular buffer. So the first in will be the first out data structure. So the pages are removed in a round-robin style. All that is required is the pointer that circles through the page frame of the process. So this is therefore one of the simplest page replacement policy to implement. So pages are removed in round-robin style. Now, the logic behind this choice, other than its simplicity, is that one is replacing the page that has been in memory the longest. So first in, first out. The page fetched into memory a long time ago may have now fallen out of use. This reasoning will often be wrong because there will often be regions of a program or data that are heavily used throughout the life of a program. Those pages will be repeatedly paged in and out by the FIFO algorithm. The next is the clock policy. So this policy again is the simplest form, and it will require the association of an additional bit with each frame. And this is referred to as the use bit. Now, when a page is first loaded into a frame in memory, the use bit for that frame is set to 1. Now, whenever the page is subsequently referenced, that's after the reference that generated the page fault, its use bit is set to 1. Now, for the page replacement algorithm, the set of frames that are candidates for replacement, this process can be the local scope, or all of the memory global scope is considered to be the circular buffer with which a pointer is associated. Now, when a page is replaced, the pointer is set to indicate the next frame in the buffer after the one which has been updated or just updated. Now, when it comes to time to replace a page, the operating system scans the buffer to find a frame with a use bit set to 0. Now, each time it encounters a frame with a use bit of 1, it resets that bit to 0 and continues on. Now, if any of the frames in the buffer have a use bit of 0 at the beginning of this process, the first such frame encounter is chosen for replacement. Now, if all of the frames have a use bit of 1, then the pointer will make one complete circle through the buffer setting all the use bit to 0 and stop at its original position. Now, replacing the page in that frame, we can see that this policy is similar to first in, first out, except that in the clock policy, any frame with a use bit of 1 is passed over by the algorithm. So the policy is referred to as a clock policy because we can visualize the page frame as layout in a circle. And also a number of operating systems have employed some variation of this simple clock policy. So the figure here again provide an example of a simple clock policy mechanism. We can see a circular buffer with n. We have n main memory frames is a variable for page replacement. Now, just prior to the replacement of a page from the buffer with the incoming page 727, with incoming again page 727, the next frame pointer points to frame 2. So that will point to the first frame in a circular buffer frame that are candidate for replacement. So the use, which contains again page 45. Now the clock policy is now executed. Because the use bit for page 45 in frame 2 is equal to 1, this page is not replaced. Then instead, the use bit to set to 0 and the pointer advances. Similarly, the page 191 in frame 3, we have the 45 previously. Now page 191 in frame 3. So our frame numbers are 0, 1, 2, 3 outside, and the pages numbers and the use are inside. So page 193 in frame 3 is not also replaced because again, the use bit is 1. And its use bit now will be set to 0. And the pointer will advances. In the next frame 4, the use bit is set to 0, which is frame 4, set to 0. Therefore, page 556, which is the use bit is 0, is replaced with page 727. And the list, then we keep going. Now the use bit is set to 1 for this frame, and the pointer advances to frame 5, completing the page replacement procedure. So the behavior of the clock policies is shows in our previous figure 1.4, which we went through. So this is the diagram showing the number of again frames allocated for all the 4 types of algorithm, the FIFO clock, least recently used, and the up to. So here we say this figure again is the comparison. So the figure 8.16 here shows the result of experiment that was reported in which they compare the 4 algorithms that we have been discussing now. Now it assumes that the number of page frame assigned to a process is fixed in this case. Number of frames is the same. And also the results are based on the execution of 0.25 times 10 to the power 6 references in a Fortran program. And here we are using a paging size of 256 words. And we can see the performance of each algorithm. So next we discuss about the page buffering. The page buffering normally improves the paging performance and also allows the use of simpler page replacement policy. So here we also say that although the least recently used and the clock policy are superior to the first in, first out, They both involve complexity and also overhead, not suffered with first in, first out. Also, in addition, there is a related issue that the cost of replacing a page that has been modified is greater than for the one that has not. And because the former must be written back out to a secondary memory. So an interesting strategy that can improve paging performance and also allow the use of simpler page replacement policy is what we call the page buffering. So here we have the replaced page is not lost, but rather assigned to one of two lists. We have the free page list, modified page list. With the free page list, the list of pages frames are available for reading in page. And also modified page list, the pages are written out in clusters. So again, this page replacement algorithm is simple first in, first out. Now, to improve performance, a replacement page is not lost, but rather is assigned to one of the two lists, either the free page list if the page has not been modified, or the modified page list if it has. We should note that the page is not physically moved about in memory. Instead, the entry in the page table for this page is removed and placed in either free or modified page. So again, the most important aspect of this concept is that the page to be replaced remains in the main memory, So if the process references that page, it is returned to the resident set of that process as later cost. And in effect, the free and modified page lists act as a cache of pages since they are in the memory. So the modified page list serves another useful function. The modified pages are written out in clusters rather than one at a time. Now, replacement policy and the cache size. As we discussed earlier also, the main memory size is getting larger and the locality of application is decreasing. In compensation, cache size have been increasing, and large cache size, even multi-megabyte ones, are now feasible in design alternatives. So again, with a large cache, the replacement of virtual memory pages can have a performance impact. Now, if the page frame selected for replacement is in the cache, then that cache block is lost as well as the page that it holds. So in systems that use some form of page buffering, it's possible to improve cache performance by supplementing the page replacement policy with a policy for page replacement in the page buffer. So most operating systems place pages by selecting additional page frame from a page buffer using the concept of, again, the first in, first out discipline. So most operating systems, as we said, place the pages by selecting an arbitrary page frame from a page buffer. Next is the resident set management. So with the page virtual memory, it is not necessary and also indeed may not be possible to bring all of the pages of a process into main memory to prepare it for execution. So the operating system must decide how many pages to bring in. That is how much main memory to allocate to a particular process. So several factors have to be considered here, since the operating system must decide how many pages to bring into main memory. So the first, again, is the smaller the amount of memory allocated to a process, the more processes that can reside in memory at any one time. This will increases the probability that the operating system will find at least one ready process at any given time. And this will reduce the time lost due to swapping, since again, all the processes are in the main memory. Now, second option is if a relatively small number of pages of a process are in main memory, then despite the principles of locality, the rate of page fault will be rather high. And also beyond certain size, additional allocation of main memory to a particular process will have no noticeable effect on the page fault rate for that process. Again, because of principles of locality. Next, the residence set size. With these factors in mind, then two sorts of policy are to be found in any contemporary operating system. One is the phase allocation policy, which normally gives a process a phase number of frames in a main memory within which to execute. That number is decided at initial load time, that is during the process creation time, and also may determine based on the type of process, either interactive or batch, or any type of application, or maybe based on the guidance from the programmer or system manager. Now, with a phase location policy, whenever a page fault occurs in the execution of a process, one of the page of that process must be replaced by the needed page. The second option is the variable allocation. This allows the number of page frame allocated to a process to be varied over the lifetime of the process. So here, a process that is suffering with high level of page faults indicate that the principles of locality only holds in a weak form for that process, and will be given additional page frame to reduce the page fault rate. Whereas a process with exceptionally low page fault rate, indicating that the process is quite well behaved from the locality point of view, and will be given a reduced allocation with the hope that this will not noticeably increase the page fault rate. So again, the use of the variable allocation policy relates to the concept of replacement scope, as we're going to explain in the next section also. Here we can say that variable allocation policy will appear to be more powerful one comparing to the phase allocation. However, the difficulty with this approach is that it requires the operating system to assess the behavior of active processes. So the next will be the replacement scope. So the scope of replacement strategy can be categorized as global or local. We have local chooses only among the resident page of the process that generated a page fault, and global will consider all the unlocked pages in main memory. So both types of policy are normally activated by page fault when there are no free page frames. So again, there is a correlation between replacement scope and also the resident site set size. So example, we have the phase allocation, local replacement, global replacement. So with the phase allocation, the number of frames allocated to a process is phase. Pages to be replaced is chosen from among the frames allocated to that process. When it comes to global replacement, that's not possible with phase. But with variable allocation, global replacement, the pages to be replaced is chosen from all available frames in the main memory. So this will cause the size of the resident set of process to vary. And with the local replacement, again, the number of frames allocated to a process may be changed from time to time to maintain the working set of process. Also, the page to be replaced is chosen from among frames allocated to, again, that process. So next is the phase allocation and local scope. Here we say with the phase allocation policy, it is necessary again to decide ahead of time the amount of allocation to give to a process. This could again be decided on the basis of the type of application and also the amount requested by the program. The only drawback to this approach is twofold. If allocations tend to be too small, then there will be a high page fault rate, causing the entire multi-program system to run slowly. Or if allocation tend to be unnecessarily large, then there will be too few programs in main memory, and there will be either considerable process idle time or considerable time spent in swiping. So that's increasing the time spent swiping if allocation is too large. And if allocation is too small, again, there will be a high page fault rate. Next is the variable global scope. Here we say it's very easy to implement and also adopted in a number of operating systems. The operating system will maintain a list of free frames, and the free frames added to the resident set of process when the page fault occurs. So at any given time, there are a number of processes in the main memory, each with a certain number of frames allocated to it. Typically, the operating system also maintains a list of free frames. In this case, when a page fault occurs, a free frame is added to the resident set of the process, and the page is brought in. When a process also experiences a page fault, it will gradually grow in size, which should help reduce overall page fault in the system. And we have for the local scope, variable allocation, local scope. And here we say that again, the variable allocation, local scope strategy normally attempt to overcome the problems with the global scope strategy. And this will be summarized as, and when a process is loaded into main memory, allocate to it a certain number of page frames as its resident set based on application type. Then the program request or other criteria. Use either pre-paging or demand paging to fill up the allocation. Now, when a page fault occurs, select a page to replace from among the resident set of the process that suffered that fault. Now, from time to time, we are going to reevaluate the allocation provided to the process and also increase or decrease it to improve the overall performance. So decisions to increase or decrease the resident set size, again, will be based on the assessment of likely future demands of active process. So the key element we may consider is the criteria which we use to determine the resident size and also the timing of changes. Then we have the page fault frequency, PFF. So again, an algorithm that follows this strategy is the page fault frequency algorithm. Normally, it requires the use bit to be associated with each page in memory. The bit is set to 1 when the page is accessed. When a page fault occurs, the operating system notes the eventual time since the last page fault for that process. And this could be done by maintaining a counter of page references. Now, a threshold F is defined. Now, if the amount of time since the last page fault is less than F, then the page added to the residence set of the process. Otherwise, we are going to discard all pages with a use bit of 0 and shrink the residence set accordingly. At the same time, reset the use bit on the remaining page of the process to 0. So this strategy can be refined by using two thresholds: an upper threshold that is used to trigger the growth in the residence set size, and also the lower threshold that is used to trigger the contraction in the residence set size. We also have, again, the variable interval sample working set. This normally evaluates the working set of process at sampling instances based on elapsed virtual time. And this is normally, again, driven by 3 parameters. The first parameter is, again, the minimal duration of the swapping interval. And the second is the maximum duration of the sampling interval. I mean to say sampling interval. The third is the number of page faults that are allowed to occur between the sampling instances. So again, an approach that attempts to deal with this phenomena of interlocality transition with similar relatively low overhead to that of PFF is this variable interval sample working set, or VSWS. As we said, again, the VSWS policy evaluates the working set of a process at sampling instances based on elapsed virtual time. So at the beginning of the sampling interval, the use bits of all the resident pages for the process are reset. And at the end, only the pages that have been referenced through the interval will have their use bit set. So these pages are retained in the residence set of the process throughout the next interval, while the others are discarded. So next we talk about the cleaning policy. Here we say concerning with determining when a modified page should be written out to a secondary memory. So that's the concept of cleaning policy. The cleaning policy is opposite, again, of the fetch policy. The cleaning policy is opposite of the fetch policy because it's concerned with determining when the modified page should be written out to a secondary. So again, it is concerned with determining when a modified page should be written out to a secondary memory. Now, two common alternatives are demand cleaning and also pre-cleaning. So we have the demand cleaning and pre-cleaning. Now, with demand cleaning, a page is written out to a secondary memory only when it has been selected for replacement. Again, a secondary memory means it can be the hard disk, secondary storage device, which means it's taken from the primary main memory. And also the pre-cleaning policy writes modified pages before their page frame are needed, that pages must be written out in batches. So both pre-cleaning and demand cleaning have a drawbacks. With pre-cleaning, a page is written out but remains in memory until the page replacement algorithm dictates that it is to be removed. So pre-cleaning allows the writing of pages in batches, but it makes little sense to write out hundreds or thousands of pages only to find out that majority of them have modified again before they are replaced. So the transfer capacity of secondary memory is limited and should not be wasted with unnecessary cleaning operations. Also, on the other hand, with demand cleaning, the writing of a dirty page is coupled to and precede the reading in of a new page. So this technique may minimize page write, but it means that the process that suffers a page fault may have to wait for 2-page transfer before it can be unblocked. And this may again decrease the processor utilization. So we can say that the better approach now is to incorporate the page buffering concept, because this will allow the adoption of the following policy: create only pages that are replaceable, but decouple the cleaning and replacement operation. So with page buffering, the replaced pages can be placed on two lists, modified and also unmodified. So the next is the load control, which is concerned with determining the number of processes that will be resident in the main memory. So the concept of loading, so which has been referred to as multi-programming level. So the load control policy is critical in effective memory management. If too few processes are resident at one time, then there will be many occasions when the processes are blocked and much time will be spent in swapping. On the other hand, if too many processes are in resident, then on average, the size of the resident set of each process will be inadequate, will not be enough, and there will be a frequent faulting that will occur. This can result in a trashing, which we discussed in our previous lecture. Now, if the degree of multi-program is to be reduced, or one or more of the current resident process must be suspended or swapped out. So again, if the degree of multi-programming is to be reduced, then one or more of the currently resident process must be suspended or swapped out. So the lowest priority process, this will implement a schedule policy decision and is unrelated to performance issues. We also have the faulting process. The reason is that there's a greater probability that the faulting task does not have its working set resident, and the performance will suffer least by suspending it. So these are the 6 possible lowest priority process: faulting, the last process activated, process with smallest resident set, largest process, and process with largest remaining execution window. So process with the smallest resident set, this will require the least future effort, to reload. However, it penalizes programs with strong locality. Largest process, this normally obtains the most free frames in an overcommitted memory, making additional deactivation unlikely soon. So process with, again, largest remaining execution window. In most processing scheduling scheme, a process may only run for a certain quantum of time before being interrupted and placed at the end of the ready queue. And this again will approximate the shortest processing time first schedule discipline. So again, this will be our last conclusion of virtual memory chapter 8 course. So again, wish everybody the best and thank you. We should see the homework assignment on chapter 8 as soon as possible.